second most abundant natural polymers, and it can be used and improve the sustainability of the plastics by decreasing the dependence to fossil-based materials.
My name is Omid Hosseinai. I work as a researcher at Rice Research Institute of Sweden. I work on biomass valorization, bio-based material, especially lignin-based materials. So we work on different materials or different products from lignin. So what is needed is to modify lignin based on the target application. For example, if you want to make fuels or chemicals from lignin, other materials like thermoplastics or different carbons from lignin.
We are at our laboratories at Drottning Kristinas väg, where we modify lignin and we make coatings with it and coat paper and board with lignin.
This is one of the wet spinning labs at Rice. Here we develop fibers from renewable sources, mainly from lignin and cellulose. The fibers can be used in several applications. For example, as a precursor for carbon fiber, textile fiber development, and also fibers for biocomposites.
So one area we work is carbonized materials from lignin, and one application of the carbonized or material is using this material in energy storage application. I mean, you know that the demand for energy is growing and the need for the renewable sources or more efficient ways, for example, using batteries for storing the energy is increasing. So here is this is the car that we, as a demonstrator, we made it. So in this car we have different components made from lignin-based carbons. For example, the roof of this car is made from the lignin-based carbon from the melt spinning process. And also in this car we have lithium-ion batteries, and these batteries are inside the car, and in these batteries we use a lignin as anode electrode for the lithium-ion batteries. This is to show different applications from lignin, both structural and non-structural, which is energy storage applications.
My name is Erik, and I work as a research engineer here at Rice, mainly with chemical analysis of samples from the pulp and paper industry. One of our techniques that is very useful is pyrolysis GCMS, in which the samples are heated rapidly to high temperatures in an inert environment. In that way, we can identify the chemical structure of any organic material, such as lignin.
Lignin is a fantastic material. It's beautiful, it's brown like chocolate, and it's full of functionality, so we can do a lot of wonderful things. And we just need to be each day smarter about this. It's fantastic.
So good afternoon and very welcome to today's webinar from Lignin. I hope you enjoyed the film from my colleagues at Rice and got inspired on what we can do with lignin. And today's topic is using lignin in transportation fuels. I am Maria Almholt and I work as a project manager at Rice testbed Lignin. And we run a collaborative project called Lignin Innovation, and thanks to that we can present those webinars. The project is financed by the EU Structural Funds Program, Region Värmland, and also by the project partners, Paper Province and the Kristinehamn Municipality. It's a 2-year-old project which focus on digitization and also to be more international. And also today's webinar is recorded, so if you want to see it again, then do so at our website, Lignin. If you have missed the previous webinars, you can also find them there. But today we are happy to present from Rice Linda Sandström and Erik Furusjö. And they will tell more about how to use lignin. Our next event is for ladies only, because we do that on the 8th of March. So if you are not a woman yourself, please recommend all the women you have around you to join us on the 8th of March to celebrate women in science. But today, for the equality, Erik, I hope you are ready to start with your presentation and also tell us more about who you are.
Yes, I am. I hope you can hear me.
Definitely. And see you as well. Perfectly.
Perfect. Great. Thanks. So my name is Erik Furusjö. I work as a researcher within the biorefinery area at RISE. I'm also responsible for managing the focus area, biorefinery and renewable fuels at RISE. And also have a part-time assignment as an adjunct professor at Luleå University of Technology in energy technology. So I work with biorefineries and converting different types of biomass to biofuels and bio-based chemicals. And of course, lignin is one of the relevant components in this area. I will start to give a more introductory view to biofuels from forest-based biomass, including some aspects of lignin, and then Linda, who will talk after me, will be more specific about experimental technologies and results from that. But with that said, I hope to be able to answer also questions about specifics. But I will start to share my screen.
Yeah, and meanwhile, then I let you all know that if you have questions to Erik or Linda, you are free to write them in the chat function. You find it at the bottom of your screen. Just press there, and you can type any messages you like. And also today, when we are finished at 3 o'clock, you are welcome to stay if you want to, and we open for a discussion. But during the webinar, the recommendation is to use speaker's view. Then you will see who speaks next to the slides being showed at the screen. And you find where to change the view in the upper right corner. Now, Erik, we see your screen perfectly well. So please let us know more.
Thank you. So I have given this short presentation the title Resource Efficient Use of Forest Biomass, Biofuels from Residues and Byproducts. And there are, of course, many ways to, start this subject. But one important aspect that makes this topic of resource efficient use of forest biomass important is the current debate about sustainability of forest biomass and potential conflicts between forest biomass use, biodiversity. And of course, I'm not an expert in that area. I'm not going to enter that debate. But what you can say is that regardless of where you are in that debate, you can say that if you can maximize the utility, the benefit of each tree that you harvest in the forest, then that is a good thing. So resource efficiency in terms of biomass use, maximizing the products that you can produce from this forest biomass and maximizing the amount of fossil products that you substitute is always a good thing. And that is sort of what I'm going to speak about today. And if you look at the typical traditional forest value chain, then you can say that you have the forest, you harvest the trees, you send them typically to sawmills and pulp and paper mills, depending on dimensions. And then you make products like paper, packaging, construction timber, and so on from sawing. And in this process, you also burn a part of the biomass to give the energy needed in the process. So typically you burn bark or sawdust or chips in the sawmill, and you burn black liquor and bark potentially in a pulp mill. And that emits CO2, of course. So part of your feedstock does not go into, part of the carbon in your feedstock does not go into products, but instead it is used for energy purposes and becomes carbon dioxide in the process. And then there is, of course, the potential to not use all your byproducts for energy. There's also the possibility to extract from this value chain byproducts and residues. For example, forestry residues from the forestry, so tops and branches. From the pulp mill, you can, if you have a pulp mill that is for sort of energy sufficient, you can export perhaps bark and perhaps lignin, for example, also. And that is currently mostly used for energy purposes. So if we export that, we use it currently mostly to produce heat and sometimes power, depending on if it's in a combined heat and power or if it's in a small boiler or something like that. But in that case also, the carbon is not used. We use the energy, CO2 becomes carbon dioxide. What we are working with is, of course, to try to increase the use of the biogenic carbon in the forest material. So essentially trying to use these residues and byproducts in other types of processes than combustion for energy purposes. So what I've entitled the box new biorefinery here. So converting them into biofuels, chemicals, biomaterials, different types. And lignin is one of these, but also the other byproducts can typically be used for these. But of course, also sometimes some of the carbon is lost in these materials, and you produce CO2 or you produce other residues that needs to be incinerated. But essentially, what you can say is that in this chain, if you can maximize the amount of the carbon in the starting forest feedstock that goes into the right part of the picture, so into products, rather than into CO2, then you maximize the carbon efficiency, and then you also, what I claim, maximize the utility of the tree that you harvest. Of course, energy is also utility in itself, but in the long term, the substitution effect will be larger for creating carbon-based materials than for creating heat from biomass. Heat can be created in other ways that are also sustainable, easier than carbon-containing materials and molecules. So that's the starting point sort of for this. And then, of course, residue upgrading. So we want to have different processes for this new biorefinery to upgrade these residues. And I already mentioned that the most important residues from this chain is typically the forestry residues, so tops, branches, etc., bark, sawdust, and perhaps lignin if you have a pulp mill that can separate and export lignin. So is this happening? Well, yeah, sort of. These are different projects. Some of these news are in Swedish, unfortunately. And they also represent different, how do you say, stages of realization. For example, to the left, we have an example with sawdust that is a reality today. That is the pyrolysis plant for sawdust from a sawmill that Furusjö, which is a joint venture between Setra and Prim, has built in the Kastet sawmill outside Gävle in Sweden. And then this oil, pyrolysis oil, so they liquefy the sawdust, and then this pyrolysis oil is sent to a refinery where it is upgraded to biofuels. So that is an example of a value chain that is in commercial, or at least close to commercial scale, for sawdust to biofuels. Then the second example for lignin is something that is not in the same stage of realization. This news is from 2018, and it says Prim will build a new factory for biofuels from lignin with a Swedish startup, and the Swedish startup is Renfuel. And what Renfuel is to have a technology to make lignin compatible with oil refineries. And the plan was to build a lignin separation and derivatization plant in the Vallvik pulp mill in Sweden. Now that has not happened, and we're still waiting for the first plant with this technology to be arisen. But it's also a possibility that is being trying to be commercially deployed. And the third example to the right is another project that is only in the engineering stage, which is a plan for a plant to gasify forest residues and bark to produce biojet fuels, so for sustainable aviation fuels from forestry residues then. That type of process is not yet being deployed large-scale commercially, at least not in Europe. The first plants are under construction in the US. So it's also something that is sort of up and coming. So these were some generic examples for different types of residues. If we go specifically more into lignin, what are the possibilities? And here I'm gonna separate into two different types of lignin. The type of lignin that I have talked about up to now is kraft lignin. So it's lignin from pulp mills. The type of lignin that is present in black liquor, which you get when you pulp wood and produce pulp for paper, and that can be separated from black liquor. And today, commercially, there is only two lignin separation plants present commercially, and the rest of the, so practically all of the black liquor produced, and thus all of the lignin produced in pulp mills is incinerated. And this is substantial amounts of energy. In Sweden, it's about 40 terawatt hours per year, and globally it's about 800 terawatt hours per year. If you want to provide some context to those numbers, and 40 terawatt hours per year is about half of the energy consumption in the total Swedish transport sector. So it's a lot of energy. This type of lignin is not no longer so similar to native lignin, to wood lignin, because it's in the process it becomes condensed, which means that it's quite non-reactive, difficult to do things with compared to other lignins, and also it contains sulfur from the pulping process. So the types of processes that you have to use have to take this into account. And there are some different ways to upgrade this to fuels and chemicals. I mentioned Renfuel in the previous slide, and what they do is that they do a chemical modification of the lignin to make it more compatible with the type of processes that you have in a fossil refinery. Essentially, they modify the lignin chemically so that you can mix it with fossil components and upgrade it to biofuels. Sun Carbon is another Swedish company that had another process to also try to make lignin compatible with the refineries. They are also now focusing on more on other areas of lignin application. But you have to do something with the lignin to get it into a fossil oil refinery, or you have to use what I call robust catalytic upgrading methods, so non-conventional methods that are not present in fossil oil refineries. And Linda, who talks after me, will talk a little bit more about this. So other technologies are needed. And this is, of course, a marked difference compared to the currently mostly used biofuel in Sweden, which is HVO, which is hydrotreated vegetable oils, which are much more, those processes are, that is much more similar to fossil feedstocks, and those processes are much more similar to the kind of processes that you have in a fossil refinery, even if, of course, it's not exactly the same. But lignin, you cannot put into that process without doing this type of modifications. This condensed nature and non-reactive nature also makes like thermochemical upgrading, so processes like they're called gasification or pyrolysis of lignin, kind of difficult. I should say impossible, but at least difficult. But what has been proven is that you can actually gasify the black liquor without separating the lignin first, and then it's much more reactive because it's in a solubilized form with a lot of sodium salts that act as a catalyst in that gasification process. And this has been proven then in pilot demonstration scale, both by Chemric in Sweden and by TRI in the US. Long time ago. Then we have the other type of lignin, which is biorefinery lignin, and that's the type of lignin that you get from the biorefinery process, so not from a traditional pulp mill. Essentially, when you use woody biomass for a secondary biorefinery, one of the possible technologies is to use what we call the sugar platform. So sugar-based upgrading, then you want to have the cellulosics for sugar, and then you separate the lignin by various pre-treatment techniques. And then you get what I call biorefinery lignin. And the nature of this is very different depending on the separation technique you use between lignin and cellulose, of course. But generally, these lignins are much more reactive than kraft lignin. So you can use other types of processes in an easier way than with kraft lignin. And I should also mention that, of course, this technology is going to be, development of upgrading of this type of lignin to fuels and chemicals is going to be very important in the total economics of these secondary biorefineries, since lignin is a large part of the wood. So if you can valorize also that part of the feedstock and get a valuable product instead of only heat by burning it, then of course your total production economics will improve. And here many upgrading technologies are being tested, but it's still a little bit less mature than the technology, some of the technologies that I spoke about earlier for kraft lignin. And then if you go into these upgrading techniques and more general, so if you take a step back and no longer talk specifically about lignin, I'm gonna end this presentation by talking a little bit about how you can improve resource efficiency in the residue upgrading to biofuels itself. I mentioned when I had the slide with the value chain that even if you take the residues down to this box called new biorefinery and transform it into biofuels, typically quite a bit of the carbon in the feedstock for that process, which is the residues then, so which might be sawdust or lignin or or forest residues is lost into carbon dioxide or other byproducts. And if we want to maximize the efficiency of that one, of that process, that is also important, of course, to maximize the total utility of harvesting our tree to start with. And then there are different approaches. Typically, I mentioned here some of the technologies that I have spoken about earlier. I have gasification, liquefaction, and upgrading, and second generation ethanol, so sugar platform, and typical carbon efficiencies for these. So of the feedstock that you put into the biorefinery, so from the sawdust or from the forest residues, how much of the carbon that ends up in the product? And as you can see, it's typically between, say, 25 and 50%. So we use between 1/4 and half of the carbon in the feedstock to product. The rest is converted either to CO2 or to byproducts with lower value. Obviously, we would want to increase this to get more product from the same amount of feedstock. And then there are different ways. And this picture to the left illustrates part of what you can do with CO2. So you emit CO2. That is because you typically use part of your feedstock for energy, whether you burn the lignin in a second generation ethanol plant to get heat for your pre-treatment and for your distillation, or whether you use gasification, where you pass the energy in the process to get or in the feedstock to get the process temperature you need, which is typically very high for gasification. Then it becomes CO2. And then there are different options. Of course, you can capture and store this CO2, and that's what we call BECCS, so bioenergy carbon capture and storage. There's also the potential to use bioenergy carbon capture and utilization. So that case, you upgrade the CO2 typically with hydrogen to more fuels. But what I'm going to talk about a little bit about now is this third arrow. That really means that it's drawn like the CO2 goes completely back into the plant, but actually it's about avoiding the CO2 being formed in the first place by electrifying the process partly. So this is a type of technologies where partial electrification of biorefineries can greatly improve the total carbon efficiencies of those biorefineries. And the reason is twofold. I already mentioned that you typically use part of your feedstock to supply the energy for the process, whether it's for ethanol distillation or whether it's for gasification process temperature or something else. And then obviously, of course, electricity can provide energy instead of burning part of your biomass if you think biomass is a more limited resource than electricity. But it's also the fact that typically you want to make products that are hydrocarbons that fit into our current energy system and our current chemical plants, and they typically have a hydrogen carbon ratio of 2, so it's 2 hydrogen atoms per carbon, while biomass typically has a hydrogen carbon ratio of 1 approximately. So that means that if you don't add extra hydrogen, you simply cannot utilize all of your carbon. Well, we know that hydrogen can be made from water electrolysis by adding electricity. So essentially, these electrification technologies have many variants, but the two most important are either providing heat by either heat pumps or direct heating, or by adding an electrolyzer and adding hydrogen. And what we can see here in this graph to the left, we'll finish after this, is that essentially we have, now this is in Swedish again, but the x-axis label says fraction of electrical energy in the input to the biorefinery, and that goes from 0 to about 70%. So 0% means that you only have biomass into your refinery, and then we see that the carbon efficiencies, which are on the right axis, typically are between 30 and 50%. Well, that's what I said on the previous slide. That's the carbon efficiency you get. But while you start adding electricity, this drastically increases if you do it in the right way. And when you add about 60 to 70% electricity, you can typically get close to carbon or 100 or even above 100, which is an artifact of integration. Carbon efficiency, you can transform all your carbon in your feedstock into product. Now, of course, the question is if this is no longer if this is a biofuel or if it's something else, because the 2/3 of the input in that case is electricity and not biomass. But what I want to highlight is that in increasing the resource efficiency in the total value chain from forest to various carbon-containing products, then electrification can be an important part. This was for the biorefinery, but the same might well be true for the pulp mill. Decrease incineration, export more byproducts that you can turn into carbon-containing final products. So to summarize, what I have presented now is that increased biomass resource efficiency, which is sort of the topic that I have spoken about, contributes to climate benefits, and it contributes to a higher production potential for biogenic products, biogenic carbon products. You can make more products from the same amount of biomass feedstock, so from every tree that you harvest. And my absolute belief is that this will be a competitive advantage in the long term when biomass resources become even more asked for, higher demand than today, and thus even more limited in supply compared to demand. Might even be a requirement. We will not tolerate that half of the tree that we harvest, which is valuable, ends up as CO2 that goes directly up into the atmosphere. And residue upgrading is an important way to increase this resource efficiency, and lignin separation from pulp mills is an excellent example where you can turn this into hydrocarbon product instead of burning it. And in the long run, I'm convinced that we will burn less biomass for heat and electricity. Electrification is a way to increase the carbon efficiency in this forest value chain, and especially lignocellulose-based feedstocks like forest-based feedstocks has a great potential in this field. That was what I planned to say. Maria, do you want to take some questions from the chat directly, or what is your plan?
Yeah, we thank you first, Erik. Great to listen to you. And yeah, we do have some questions. The first one is, how does sulfite process lignin fall into this classification?
Good point of view, good front. I must say that I don't know exactly how reactive and how that would behave in some of these processes. I mean, it has been attempted for gasification that works well. Gasifying sulfite liquor works as well as gasifying black liquor. It's typically exported as lignosulfonate today. Then I don't think reactivity is so important. So I must say that I don't know, but I'm sure I have colleagues who know, so I can check and reply later.
Thank you. And next is more a quote from a follower, but a question. But I will read it, and you can reflect and comment. Yeah. So I read, Erik, you seem to be on a mission to talk about the biocarbon mass balance. You did that in your talk at Ekman-dagarna. This is a neglected subject, I think, and this is the person writing point of view, of course, and I think that every bio-based process making fuel or materials should demonstrate where every carbon atom in the raw material ends up. Biocarbon efficiency should be a key parameter when, for example, grants are being allocated, and that's more a person's reflection than a question.
Yeah, but I think it's more a confirmation of the message I tried to give today. I feel exactly the same. I think biomass has a great potential to contribute to the transformation to a climate neutral society, but the supply of sustainable feedstock will always be limiting, and then it's going to be mandatory to use the feedstock that we have as efficiently as possible.
Thanks. And this one is also interesting. What is the impact in the economics of the product when you have increasing input of electricity?
Good point. Good question. That depends a little bit on the type of electrification technology. And of course, if you have an electrolyzer involved, then it pays greatly on the cost of the electrolyzer. In general, we can say that what I had in my slide was not economics, but I had total energy efficiency, and that's also an important aspect. And what that slide shows and what the results from the project that I cited shows is that the total energy efficiency does not change so much. So that's about the same. So you still have about the same total conversion of energy, whether it's only biomass or biomass plus electricity into products. Now for cost, typically when you look at the current predictions for electrolyzer costs and electric heating costs in the at least next 5 years or 5 to 10 years, then the cost is going to increase a little bit. Not dramatically, but a little bit. But I think the relevant comparison here is to make to electrofuels or power to liquids, or what we call it, so transforming CO2 to namely. And then we are still below that cost, because that cost is substantially higher than biomass to liquids today. So what we end up when we partly electrify biorefineries is somewhere in between a biomass to liquids plants and a power to liquids plants, and that goes both for the sort of concept and for the cost.
Thanks. Then we have a long story here from our colleague Per Tovani. So I haven't been able to read it through before, but we listen. Biorefinery lignins is quite a family of lignins. Smile. Is the biorefinery lignin from a strong acid biorefinery process more reactive than a kraft lignin and less condensed? And how much lignin are we talking about in biorefinery lignins in general? A kraft lignin is about 90 to 98% lignin and contain only traces of carbohydrates, depends on the wood species. Is it so that the carbohydrates in biorefinery lignin, which not is as pure as a kraft lignin, contribute in your conclusion about reactivity?
Absolutely, that's definitely true. It's a fact that it's easier to upgrade a lignin cellulose or lignin or cellulose residue mixture than pure lignin, which is a part of the explanation, but not only the explanation. And there are also biorefinery lignins that are fairly pure, for example, from some organosolid processes that I include in biorefinery lignins. So maybe I should have emphasized more that biorefinery lignin, I said that the properties vary depending on the pretreatment and separation process that you have, and perhaps I should have emphasized this more, but definitely, Per, you are right that it's not only the lignin, but also what it's mixed with that contributes, because there are interaction effects when you treat this.
Thank you. One more short one, and then we hand over to Linda. The last one, on structural basis, which lignin is best, biorefinery lignin or kraft lignin for making fuels?
I don't think any is best. It's that you have to adapt the type of process that you use to your feedstock so that it's fit for purpose. But I mean, best would also mean today, the potential or the supply of kraft lignin is much higher because there are not that many second generation ethanol plants that can export lignin, for example. While typically with some technologies, you can say that more reactive means more easy to transform. So it could be, but it has been shown in the examples I gave that also kraft lignin can be transformed. So I don't want to pick a best.
Thank you very much. You will stay with us online and also be available a few minutes after 3 o'clock for an open discussion if anyone likes to. But we also have Linda with us from RISE. How are you, Linda?
Yes, thank you. I'm fine.
Good. And you are ready to take over and
yes.
present your screen and also present yourself, who you are and what you are doing. And thanks to everyone who's been asking questions. Same follows. You type your questions in the chat and we will respond to as many as we can. And after 3 o'clock, we will stay online, whoever wants to, and we can have an open discussion. Please, Linda.
Okay, thank you, Maria. My name is Linda Sandström. I am director of a unit at RISE called Sustainable Energy Conversion, and also a researcher. And the title of this talk is Conversion of Lignin to Transportation Fuels, Activities Performed at RISE. And by activities, I mean experimental activities. So that will be the focus of my talk. And I will start a bit with the broader picture and look at what we do with bio-based feedstock in general, but I will also touch upon where lignin fits in this process and give some lignin examples in the end. So if we look at any bio-based feedstock, it can be liquefied into a bio-oil by pyrolysis or by HTL process. It doesn't have to be, it can also be directly upgraded in an upgrading process, for instance, at a refinery, or this bio-oil, bio-crude can be upgraded. And the upgrading process can be together with fossil feedstock at a fossil refinery, but we also look into pure bio-based processes to look at new ways to convert biomass into transportation fuels. Another way to upgrade biomass to fossil feedstock, which Erik also mentioned, or to transportation fuel, which Erik also mentioned, is gasification where you transform it into a syngas, carbon monoxide and hydrogen, which can then be synthesized into chemicals and fuels. So that is kind of the broad picture. And if we then look at liquefaction, we have hydrothermal liquefaction. At RISE, we have both small scale semi-batch and continuous pilot scale equipment. And the biomass that you feed into this process is wet, and the conditions are near the critical point of water. So it's quite high pressure in these processes. And the bio oil, or often called biocrude, that you produce has reduced oxygen content and metal content compared to the feedstock. And if we talk about lignin, HCl works well for these biorefinery lignins or hydrolysis lignins, but it's perhaps not the best option for kraft lignin, I would say. Another liquefaction technology is pyrolysis, and we have various test beds at RISE for pyrolysis of both biomass and plastic waste in various scales and modes, from analytical scale up to pilot scale, and both continuous and batch, and some have the possibility to add a catalyst. So here we can produce pyrolysis bio-oils in various amounts from biomass feedstock. And pyrolysis of hydrolysis lignin or some of these biorefinery lignins may be possible. Pyrolysis of kraft lignin, if you want to produce a liquid with a high yield, is very difficult. So that is perhaps not the best option either. Gasification, Erik mentioned black liquor gasification, but we at RISE, we have a number of gasifiers from fundamental research scale up to about 200 kilowatts, the gasifier shown in the picture. And if you produce a syngas, you can use it then for various applications. For instance, production into biofuels and or chemicals. And as Erik said, black liquor can be gasified. Pure kraft lignin is perhaps more difficult to gasify. But lignocellulosic biomass is a good feedstock for a gasifier. So what do we do with the lignin then, which is a little bit difficult in many of these pre-treatment processes? Well, we can hydroprocess it, treat it with hydrogen and a catalyst at high or relatively high temperature and pressure. And the simplest way to do that for screening of conditions is to do it in a batch autoclave, where you fill the autoclave with the biomass and a catalyst, which is then fine particles of a catalyst. And then you can have also, if the biomass is a powder like lignin powder, you can also add a liquid co-feed if you want to. And then you pressurize with hydrogen and heat this to your reaction temperature. Then you keep it at your temperature for a while and then cool it down. And then in the best case, you have this nice fuel product, which you can see to the far right in this picture. However, this process does not perfectly simulate the conditions that would be in an industrial hydroprocessing unit. So it's good to continue the testing in some kind of flow mode reactor. So then we have fixed bed tube reactors, which are filled with supported catalyst pellets, which you can see an example of in the picture also. So then you feed your feedstock continuously through this reactor and through the catalyst bed. For this type of setup, it's good that the feedstock is homogeneous and one phase. So here, formulation experiments come in to make a nice feed that can run through this reactor without plugging and so on. However, these lignocellulosic feedstocks, and especially lignin, can sometimes be difficult to feed through a fixed bed reactor because they tend to form coke and plugging, melting issues that are difficult to handle. So therefore, we also study another reactor configuration, which is slurry hydrocracking. So slurry hydrocracking is a robust process, and therefore it's suitable for bio-based feedstock, which can be difficult in fixed bed reactors. This type of process is originally designed for upgrading of vacuum residue, a very heavy fossil feedstock, which is also difficult to upgrade. So it's designed to avoid problems with coking, pressure drop buildup, poisoning of the catalyst, and formation of hotspots inside the reactor, but to still ensure a high conversion. And that is why we study it for bio-based feedstock, and it has shown to be very suitable for this type of feedstock also. And we use it to study both pure bio-based feedstock, but also co-refining of bio-based and fossil feedstock. And this pilot can be run as a continuous process, but we can also run it semi-batch if we want to screen a number of parameters and feedstocks and catalysts and so on in simpler experiments. It runs at temperatures up to 500 degrees and pressures up to 180 bar. And typical feedstocks can be pyrolysis oil, lignin, solid lignin powder, HCl oil, and also then some fossil feedstock if you want to have that. Yes. So what happens in this process, as in most hydrocracking processes, is that you get thermal cracking of the molecules, so they become smaller, and you also get catalytic hydrogenation. And oxygen in the feedstock is removed as water and sulfur as H2S. Typically use molybdenum or nickel molybdenum catalysts. And in this pilot, we collect the liquid product as a heavy oil product, a light oil product, and a water phase, which you can see in the picture here, although the relative amounts in the picture here is not representative of what is formed in the process. So we run it continuously, about 1 liter slurry per hour in this pilot plant. And the catalyst is pre-mixed with the feedstock. So that was some of the experimental setups that we have at RISE to study lignin conversion and biomass conversion to fuels. Then on the analysis side, there are, of course, a number of options. So I have decided not to include them all, but just to say that there are, of course, depending on what question you want to answer, you have to do your analysis based on that. But typically we analyze elemental composition, including oxygen content. It can be interesting to see how much oxygen has been removed. Molar mass distribution, boiling point range is interesting. Look at substance classes, look at where the metals has gone in the process and the trace elements, look at where the biogenic carbon has ended up, and also some physical-chemical properties like miscibility and stability and so on. Many analyses we do in-house, but some we also send externally. And then some project examples. There a couple of years ago, we had a project called BioLi 2.0, which was for lignin into bio-based fuels and chemicals. So in this project, we studied lignin depolymerization and formulation of feeds for hydrotreatment, and looked at different catalysts and did hydrotreatment experiments. And the conclusion was that it works to convert the lignin and lignin-based bio-oils together with fossils and other renewable feed components to biodiesel. So that was a very nice conclusion from this project. It was also done some techno-economics, and it was found that the economics are challenging in relation to current fossil crude oil prices. But as we all know, if we really want to replace the fossil oil, that price is perhaps not the most relevant price to compare to. We have an ongoing project now together with Preem and Chalmers called slurry upgrading of bio-oils in a complex refinery. And this project aims to make fuels and chemicals from forest feedstock. And here catalyst development is performed at Chalmers, and then we do upgrading in the slurry pilot plant at RISE. So I have some example here with recent results that we obtained with Kraft Lignin. This pilot, it was 10% lignin in a fossil co-feed. And it was a semi-batch experiment where we wanted to avoid heating the reactor with the lignin inside. So we heated the reactor with a half full with a fossil feedstock. And then we have a continuous hydrogen gas flow through the reactor. And then when the reactor has reached the correct temperature, we fed in the lignin slurry, which then had 20% lignin, but in the resulting mixture, we had 10% lignin in fossil co-feed. And with this setup, we could get complete conversion of the Kraft Lignin to non-solid products. And also interesting here is that we used only 50 bar, which is not extremely high for a hydroprocessing process. Typically, the fossil processes are run at 150, 180 bar. And it was still a reasonable gas yield, a very low coke yield, and we got about 70% of the oxygen in the lignin was removed. So this we found very encouraging results that we will continue to work on. Yes. So thank you. That was some of what we do on lignin upgrading.
Thanks to you, Linda. And the questions are dropping in. So we start from the first one. And how far along are the bio-oil separation process?
Bio-oil separation, what do you mean with, depends what the person means with bio-oil separation.
It came rather in the beginning when you presented, so perhaps it's connected to some of the first slides. It's Joshua Nell who asked the question, so if Joshua is listening, you can come in, turn on your microphone. We park that one for now then.
Yeah, we can, yeah, I don't know, bio-oil, I mean, yeah, we can park that one and see.
Yeah, perhaps it comes up in the discussion after also. So next one, can pyrolysis oil and crude oil derived oils be compatibilized, for example, to be used together in marine transportation engines and reduce the footprint of fuel oils?
Well, the problem with the pyrolysis oil or lignocellulosic pyrolysis oil that it's not miscible with fossil oils. So that makes like mixing it and trying to combust it in an engine difficult, I would say. So you probably need some light treatment of the pyrolysis oil to make it miscible with a fossil oil in that case. But
Yeah.
or to run on pure pyrolysis oil.
Yeah. And the next one is also about pyrolysis. So why is pyrolysis process not a good option for craft? Could you explain more?
You get most, I mean, in the pyrolysis process, you want to decompose the molecules and form them into a vapor so that they can leave the reactor and be condensed as a liquid. But the craft lignin, the bonds are already quite condensed, and you don't really form these volatile molecules. You mostly form coke. So you get coke and light gases and water, and not so much liquid from the craft lignin. And you get quite some processing problems then also with clogging of equipment and so on. So it's typically difficult.
Yeah, that's the way. And in HTL process, water used as solvent at critical point, it makes some pressure issues. Why don't we select low critical point solvents?
Well, there are some studies with HTL similar processes using other solvents than water. But that's not really my area of expertise to go into pros and cons of these solvolysis processes, unfortunately. But I can get back on that one.
Thank you. And composition of product after hydroprocessing.
Yeah, I would say if you start with lignin, typically you would and want to reach a finished transportation fuel, probably you would need a two-step upgrading process. That first you do a rough upgrading, remove maybe 70 to 90% of the sulfur and the oxygen and so on, and crack it down to a bit more suitable molecule sizes. But then, I mean, a final fuel has quite high demands on content. You will need some kind of polishing process afterwards.
Right. And which product specification should be expected from the hydroprocessing? Would that be usable, for example, as jet fuel?
Yeah, again, I think you need to polish a little bit on sulfur content, for instance, to make it a finished jet fuel. But you can run it. So it's a process optimization question, how severe you want to run this slurry hydrocracking process, for instance. But you can reach a quite nice quality with some oxygen and other atoms left.
Right. And how does the oxygen content interact with the efficiency of the hydrocracking process?
Well, it consumes some hydrogen, so that's perhaps the most obvious effect that it will have. So the more oxygen you feed in, you will produce water, so you have to have a sustainable production of hydrogen also to cope with that.
And the questions keep coming in, so this creates a big interest. So great job, Linda. But could you give an insight of the hydrogen requirement quantity to upgrade lignin/black liquor?
Oh, that's also a good question. I don't have the number in my head, but we have it in our papers, so I can get back on that one also.
Yeah, thank you. Will those slides be shared after the webinar? And that question we often get. We usually don't share them, but since we have recorded the event, so whoever wants to see them again can just look at the recording, I would say. And then we have a comment just saying, very nice job, thanks, which I agree on. And more thanks for the answers you have given, both for presentation and on the papers in Energy and Fuels. And there's a new question. How do you deal with the Na, that's natrium, right, in kraft lignin in the various processes?
Sodium, yeah. I mean, the sodium and all the metals, that is something we have to look into more, actually. It's quite known on these fixed bed supported catalysts, how they are affected and deactivated by various metals. But if we look into this slurry catalysts that are non-supported, much less is known, especially when you look into the metals typically coming from bio-based feedstock. So this is something that we're currently looking more into. Where do they end up and how much do they affect the process and the catalyst?
Very good. And there is a few minutes left, but the questions from the chat we have covered so far, and we will continue with the discussion afterwards. Here we got a new one. How do you treat HTL bio oil for further processing, example, wise hydroprocessing?
Well, since I worked with the slurry hydroprocess, it's a quite nice process for HTL bio oil. But since it's quite, it can be a quite difficult feedstock. But I mean, I've seen reports of hydro treating of HTL bio oil in fixed bed also, and they have been able to run for really long times. So with the right bio oil and the right conditions, a fixed bed can be possible also.
Thank you. And when this recording is available, everyone who's been listening has been typing their email addresses properly, they will receive an email alerting that. And again, said that 8th of March, we celebrate Women in Science. So welcome Linda to join us, and welcome all women listening. And who's not a woman, please recommend your colleagues, friends, wives, daughters, cousins to join us. We will share and give and take experiences and celebrate. So with that said, I think we have covered all the questions so far. And if someone wants to stay, then please do so. And then turn on your cameras and change the view on your screen from speaker to gallery. Because then hopefully there will pop up a lot of faces that has taken the time to join us today, which is great. And thank you all for the questions that you've been typing.